To continue our meridional structures, we'll jump to the winds themselves instead of zonal winds themselves instead of the cells. So when we do cells, we looked at the zonal winds and the vertical winds. Or we looked actually at stream functions, not zonal winds. So the distribution of winds themselves shows this particular structure with weak easterlies. The negative numbers here are easterlies. So if longitude going from Greenwich meridian towards the date line is positive, then when you go east to west, winds are easterlies when they go from east to west, then they are negative along the negative direction. And you have this vertical structure that we briefly mentioned before, where we have weaker winds at the surface and stronger core of winds in both hemispheres at a height at about 200 hectopascal in the upper atmosphere, and then again weak polar easterlies that we already mentioned. That's the annual mean. When you look at the seasonal variability, obviously when the sun is to the south, the winter equator to pole temperature gradient is stronger in the northern hemisphere. So it turns out that this jet stream, this concentrated winds with tens of kilometers per hour speeds are very strong in the winter hemisphere. So in June, July, August, they're stronger in the southern hemisphere. And of course the convection also makes a difference. Convection is stronger in the winter hemisphere, in the summer hemisphere. So you can see there is a stronger zonal wind here. We will see later on that as the ITCZ moves, the northeasterlies and southeasterlies change strength accordingly. So if it moves south, then the northeasterlies get stronger. When it moves north, the southeasterlies get stronger, and convection is typically stronger in the northern hemisphere because the ITCZ is not symmetric. It's more preferentially located in the northern hemisphere. We are adding details without actually having seen everything, but just remember these structures of the zonal winds. Okay, weak easterlies, trade winds all the way up into the upper atmosphere in the tropics, and strong westerlies with these cores in the jet stream with the seasonal variability. Just like we saw temperature structure all the way into the upper atmosphere, we can do the same for the winds, and you see that the structure is now stunningly different. This figure I took from some Norwegian University website. I think it's University of Norway, whatever it is. Okay, so this identifies the subtropical jet stream, question mark here, so obviously not completely understood. This is the stratospheric winter jet stream. So the jet streams are not only in the troposphere but also in the stratosphere, with the deep penetration of the summer anticyclonic circulation. So this also changes very strongly with the season. This is being shown for June to August. If you look at the winter structure for the northern hemisphere winter structure, that's going to be very different as well. So the idea is that along with those temperature structures that we saw, there is also a very strong zonal wind structure going very high into the atmosphere, and you can see that those speeds are not very small. Okay, up to these colors of 100 meter per second. These are in the range of I don't know, 30 to 50, 60 meter per second, whereas these are much stronger. Okay, there are dynamic reasons why that happens. So this is probably induced by cooling in the polar night. Okay, so polar night is what? Basically, if you go beyond the Arctic Circle in the northern, this is the southern hemisphere. If you go beyond the polar circle in the southern hemisphere, you're going to have very strong gradients driving polar jet streams. So you can see the seasonality here again. This is the June to August. Southern hemisphere is stronger than the summer hemisphere. Okay, so I'll come to this concept of eddies in the next podcast. Just wanted to add a little bit more detail to this zonal wind structure beyond the meridional overturning and the stream functions that we saw as Hadley cell, Ferrel cell, and polar cell. Okay, so why are there jet streams? This is a very good dynamic question, so we will at least partially answer it. We'll learn the dynamics that goes with it. And just to give you a hint, that is related to the slopes of the constant pressure surfaces that we saw. When we defined geopotential height, we ended it by looking at how the slopes of constant pressures actually increase with altitude. And we said pressure gradient can be balanced by Coriolis, which means the winds got stronger with height. Remember, I mentioned vertical shear and so on. So that is related to these concept of jet streams. The horizontal temperature gradients can create vertical shears in such a system. How does that happen? We need to learn the dynamics to get there, but we are first looking at the structures to orient ourselves. Okay, we'll look at the eddies, which are also very special and useful, especially when we said winds are mostly zonal, but the transport of energy has to be meridional. So the eddies are going to play a big role in that as well.